So this next set of videos is going to talk about quantum computing. This is a topic a lot of people are very interested in, and the goal here with this set of notes is not to really turn you into quantum engineers, but just to give you an idea of the kind of things that quantum computing is claimed to be able to do that classical computing can't do, and how it has the potential to change the way we interpret computability, especially some of the very difficult problems we have. There's a lot of stuff we have to get through before we can really get a handle on how this stuff actually works and why it's different than classical computing. So I'm going to start with just a little bit of an introduction. I'm going to tell you a little bit of the history of quantum computing and a little bit of, a very surface level explanation of quantum entanglement and superposition that is needed for these computers to do what they do. But basically, the end result of this is basically quantum mechanics is weird. All right, so the basic history of quantum computing. This stuff has been theorized for a while, but only recently has it been possible to build machines that implement these theories. So some of the initial theories happened in the 1980s. Some of the mathematics behind some of the algorithms that we do are even earlier than that. There are machines today that are in the hundreds or thousands of qubits. A qubit is just a single processing element or a single atom or particle that can be turned into a superposition and then measured. This is what we're going to use actually for the quantum computing. And the first systems were only 20 or 30 years old, but now we have systems that are hundreds or even thousands of qubits, and then the connections between them and everything. Now, as you'll see, qubits are not cheap to build, and they're not easy to run. So the time between now and when we're going to have a qubit in our home, long time. One quick note here, though, because when you're looking at the kind of quantum computers that you might hear stories about in the news, sometimes you'll hear, oh, the biggest quantum computer is now 6,000 qubits, or the biggest quantum computer is now 100 qubits, and where are these differences? Well, there's two sort of different ways of doing quantum computing. The one we're going to be interested in is with quantum gates, and we're going to talk through all the intricacies of what quantum gates are and how they work. But there's another mechanism where you can connect the quantum or the qubits in an array essentially, and have them set up and solve a solution space. So it allows you to solve a very specific kind of problem much quicker than you would in classical computing, but they're not Turing complete. They're not machines that can do anything. They can only solve this one particular kind of problem. So let's start with the idea that quantum superposition is weird. There's a ton of videos out there on quantum mechanics. This shouldn't be anywhere near a solid explanation, but it gives you an idea. So in quantum mechanics, we have this idea of superposition, where you can set up a certain circumstance where a particle might be either in one state or another, right? Schrodinger's cat is the example that is often used, and in fact, Schrodinger set this thought experiment up to show how ridiculous he thought this idea was, and in fact, this idea has been proved to be true. Schrodinger's cat, of course, says you've got a box, and in that box is a vial of poison, and that vial of poison is connected to a hammer, which will break it if a certain radioactive atom decays, right? And this is a 50-50 shot, but not clear when it's going to decay. The idea of superposition is until we actually observe that particle's decay or the results of that particle's decay, it is literally in both states at once. It's both decayed and not decayed. It's a very, very strange concept. And Schrodinger's argument was, well, if that's the case, then the cat is both alive and dead at the same time. And in a manner of speaking, it is. I mean, it's really hard to get quantum effects to sort of surface themselves at the classical scale, because it all depends on when you observe the superposition, right? Anytime you take a measurement, anytime you affect it in such a way that it affects something else that can be measured, then the waveform collapses, right? The number of possibilities split down to one, and that possibility is the thing that actually happens. So we'll talk about this in a bit more detail, but essentially, for the purposes of quantum computing, we're going to take a quantum state that is sort of a 1 or a 0. This is going to be some feature of the atom or the particle that you're analyzing, and then we're going to be able to superimpose a series of states so that it can be sort of partly 1 and partly 0 in a way that allows us to do interesting calculations in math. So we'll get there, but I want to talk through a little bit more about how weird quantum mechanics is, just so we really understand how nuts this stuff is. Probably you've seen the double slit experiment. This is the idea when you fire a beam of electrons at a wall and there's two holes in the wall. If electrons are particles, then you should end up with two piles. But since you end up with a whole bunch of piles, that is indicative of an interference pattern of two wavefronts. This is how they sort of determined that electrons are waves instead of particles. And so we have electromagnetic waves and everything. It makes sense. The waves move in the different ways. We can sort of tune them and we can direct them. We know that this is how electrons travel through space. What gets weird is that if you slow the electron gun down to one particle at a time, so only one particle passes through at a time, even then, you still get this interference pattern. And the only way that's possible is if the particle, as it goes through those two slots, interferes with itself somehow. That it's a wave of probability that interferes with itself such that it lands more likely in one place on the screen than the other. And it's really, really strange. If you put a measuring device on one slot or the other, then you don't get that interference pattern. You just get a pile, as if they were always going through one or another, because then you know that the electron traveled through one slot or the other slot. This collapses the wave function, so we're measuring at a place that forces it to be in a particular state at that screen, at the slots. And that means it doesn't interfere with itself because there's no waveform to interfere with. It gets even stranger when we consider the idea of quantum entanglement, which is when two unobserved quantities are dependent on each other. So if there are two particles that are entangled, one is up, the other is down. If you entangle them without measuring them and then pull them far apart, if you measure one as up, you know that the other one has to be down. Now, there's no way to actually use this for faster than light communication or anything like that, but it does happen instantly. And it's so a very strange thing. Here's another example of how strange this stuff is. I'm going to do this in the next video.